Oh, I don't know, it's on my laptop. Hi everyone, we'll get started in just a moment. Right, so welcome everyone, and thank you everyone who's attended in person this evening. Before we get started with the evening talk, I'll just run through a couple of publicity things for the engineering group, just talking about our upcoming talks. So following this talk, our next meeting is a joint meeting with the BGA on the 12th of February. That's also at Burlington House, and that'll be on geophysics and how the new Syria C812 guidance can benefit your ground investigation. A couple of other bits of publicity of upcoming events for EGGS. In April is our annual conference at Cambridge, with the main theme of the conference being on engineering geology of the energy transition. If you want to submit an abstract to that conference, then the deadline is the 1st of March. But yeah, please be on the lookout for further publicity for that, either on LinkedIn or online on the Geological Society website. And another event coming up in the summer is the EGGS Field Weekend in June, which will be a trip down to the Jurassic Coast. But again, please keep a lookout for further publicity on that on LinkedIn, through JISMAIL and on the JobSoc website. But this evening we have Chris Power and Verity Wadesmith from Mott MacDonald and Mike Edwards from Network Rail talking to us about Network Rail Earthworks evaluations and assessments. So I'll invite the speakers up now.
Thank you. Can you hear me okay? Good. So yeah, just echo the thanks to everybody who's braved the cold to be here tonight, and for everyone who's listening online. We're going to talk about some significant changes to the way Network Rail makes decisions about earthworks. Okay. So I'm Mike Edwards. I'm a principal engineer at Network Rail. I've been the client for a substantial technical content development program over the last few years that has culminated in these changes, and it's largely been completed by a team at Mott MacDonald. And I'm joined by Chris Power and Verity Wadesmith, who are going to tell us about some of the fantastic work they've done for us. So Network Rail, we are the owner and infrastructure manager for most of the heavy mainline railway in Great Britain. We're an arm's length government body. We're shortly expecting to be subsumed into another government body, Great British Railways, which is being set up right now. For the moment, we are organised into 5 geographical regions. Within those, there are 14 operational routes, and alongside that, some national functions. In total, we have around 20,000 miles of track to worry about, and most of that is either in a cutting or on an embankment. So Network Rail Earthworks. There are about 192,000 100-metre segments of earthwork that we look after. The peak of construction was in the 1840s and 50s. Some earthworks are a bit younger, some of them are pre-Victorian. I think we judge the original railway builders somewhat harshly through the lens of a modern design code sometimes. I expect most people here are geologists or engineers and have probably at some point or other worked for a demanding, geotechnically unaware client or manager. Imagine what it was like then, when there was immense pressure to build and open railways as soon and as cheaply as possible, to firstly attract the capital investment, but then to expedite the return on capital. So really the engineers had no choice but to minimise costs through minimising energy, through minimising land take and minimising earth moving. And what we're left with today is a legacy of oversteep earthworks. So formal management of railway earthworks began in the late 1990s following a fatal accident at Gill on the Settle and Carlisle line, which had just been saved from closure at that time. The foundations were laid then for our principal controlling standard, NRL2 CIV 086, management of earthworks. And what we're talking about tonight are some substantial changes to Module 1, evaluation, and Module 2, assessment, which we'll come on to. The catalyst for such significant changes was another fatal incident at Carmont in Scotland in August 2020, where 3 people died. That was the first such incident since Gill. And there were several investigations following Carmont, but one of them, the one commissioned by our Chief Executive, Andrew Haynes, asked Lord Robert Mayor, to undertake a holistic review of earthworks management in Network Rail, i.e. the scope of that review wasn't constrained to the factors around the accident. And Lord Mayor's task force reported back the following year with over 50 recommendations for Network Rail to address. So just looking at our management of earthworks in a simplified way, we start off gathering data. More often than not, that has been using people equipped with tablets or iPads now on site, but is increasingly drawing on other means of data capture. We make decisions about earthworks in a process called evaluation, the management actions needed and the management strategies that are appropriate. We prioritise actions because we live in a constrained world and we can't do absolutely everything we would like to for our earthworks. And then finally, we get to the point where we're taking action. And that can range from rebuilding an earthwork, which is done very rarely, to writing a letter to an adjacent landowner asking them to do or not do something with drainage or vegetation management. So one of the themes of Lord Mayor's questions and recommendations was where in that procedure is the explicit calculation of slope stability? And the honest answer is, once we're already at the take action stage and once we've already committed to a renew or refurb type capital intervention and we are undertaking assessment as the basis of geotechnical design. And really strong challenge came back as to whether that can be done much sooner in the process. Can we be thinking about slope stability much more formally at the evaluation stage, which would then benefit prioritisation as well? So we have been, over the last few years with the team at MOTS, trying to address that question. And in a nutshell, what we've done is reconfigure the evaluation procedure around a novel tiered earthwork assessment approach. So what is evaluation? The definition is there on the screen. That's been consistent throughout Network Rail's history across the civil engineering assets. We're trying to take all the information and determine the actions needed to maintain safety and performance. So if you think of, I think of actions as a solution. So a solution must be to a problem, and the definition isn't explicit about the problem, but what we've brought in the new standard at its core is a concept of a geotechnical risk, aka a problem statement. So the new evaluation procedure is there on the left, and what it's all leading to is asking the evaluator to record geotechnical risks and the associated management actions to control them in a very structured way, starting with the hazard or the potential for harm, which is arising from the inherent vulnerability of the earthwork to fail by a particular mechanism, the changing circumstances that could initiate or reactivate the failure mechanism, which we call the threats. Then moving on to the loss events that might occur should the failure mechanism occur, and the potential consequences that might be realized. So the sort of aggregation of these structured and searchable risk statements across physical whole earthworks, across lines of route, across administrative geographies, then gives rise to a geotechnical risk register in a slightly different way to what most people might understand it from projects. But my view is that this will be an incredibly useful tool in the communication of risk, especially with non-geotechnical audiences, the calibration of the risk compass between different evaluators and asset engineers, and really the sort of like audit question on why are we undertaking actions and what problems are we actually solving. So the role of assessment, which is a different procedure within new 086, is to help the evaluator actually determine and formulate those geotechnical risk statements. That's rarely done at the minute, and we'll come on to why, but the whole idea of the tiered assessment framework is to give the evaluator an assessment and therefore an answer to the question of slope stability for every evaluation undertaken for any reason at any time. So assessment, we also have a definition that has been largely unchanged since the birth of Network Rail, the qualitative or quantitative determination of the stability or load carrying capacity of an earthwork. And the question really is, well, why haven't you just been getting on and doing assessments, and what is now magically different in the new approach? So let me just introduce some of that. Comes back to cost. When we are traditionally thinking about assessment, I'm sure most people have in their mind's eye skilled people using sophisticated software, trying to execute analyses like maybe limit equilibrium or finite elements or whatever to produce useful quantities like displacements or factors of safety. That requires knowledge of failure mechanisms, knowledge of the ground model, and that in turn requires expensive activities, which are especially expensive on the operational railway, like ground investigation and monitoring, certainly site inspection and desk study and so on. So the cost of all that for one of those 100-metre earthwork segments, we estimate, is broadly comparable with a refurbishment type intervention, which typically might be installing a crest drain or a localised regrade over 10 metres or something like that. So why do the assessment? Why not just do the refurb? If we were to assess all of our earthworks, the cost would be in the region of £9 to £10 billion, which dwarfs our annual all-in £300 million expenditure nationally on earthworks. So clearly we have to do something different. We can't do what we've traditionally been doing. So the new framework retains all the wonderful things that have been developed over the years in terms of traditional assessment, whether using conventional or advanced techniques, and augments that with lower level assessments, and this is sort of the nub of it, where you have to accept a trade-off of the assessment outcome certainty and the ground model maturity with a lower cost that then enables us to apply the assessment much more widely and in fact to all of our earthworks, so that going back to evaluation, we've at least got the lowest level zero assessment available to the evaluator. So I'm going to hand over to Chris now, who's going to talk a little bit more about the tiered assessment framework.
Thanks, Mike. Okay, so I'm Dr. Chris Power from Mott MacDonald. I've been involved in this work right from the start, and we're not going to go through everything that Mike's discussed there in a huge amount of detail. This being the Geological Society, there is quite an emphasis on the geological aspects of the work, but we will touch on all of it. So between myself and Verity, we're going to explain various parts of the entirety of this framework, and I find it easiest to explain it from the top down. So from the top, we have the very top being the assessment outcomes, and that is very simply, as you can see here, kind of a traffic light type outcome of either something that an earthwork that's assessed being in a satisfactory state, an unsatisfactory state, or in a state where you've not got enough evidence to make that decision one way or the other. So you're in an inconclusive state. So starting from the top there and thinking about the assessment outcomes, and I was a bit worried this would be too small to see, but the size of the screen means that you actually can see this. So this is one of the tables from the assessment guidance. And you can see at the top here, we've got those three outcome states of satisfactory, inconclusive, and unsatisfactory against a whole range of different types of assessment techniques that you might carry out across a range of different failure mechanisms. And against those, you can see the types of outputs that would put you into a satisfactory state or unsatisfactory state or somewhere in the middle. So reading across any number of those, you can see something like looking at stability against a rotational failure. You can get an output that is in a stable or unstable state, which you can then map up to satisfactory and unsatisfactory. It's looked at in two ways, really, depending on the types of assessment techniques that are carried out. You can either have the qualitative type assessment or the quantitative assessment, which Mike referenced in the actual statement of the definition of an assessment. So just to bring that into a world that you can probably rationalize a bit more easily, two examples. The first example, top left, is a stability chart with the axes of slope angle and slope height for, in this case, rotational failure. And you can see within that, this builds on work that was done over many years looking at the global stability and resilience appraisal methodology. So it's based on a whole suite of limit equilibrium calculations. You can see stability zones on that chart. To the right and up in each of those is either side of effectively every one of those boundary lines is a factor of safety of 0 in given conditions. And then you can split that zone down at the very highest level into low vulnerability, moderate vulnerability, or high vulnerability of failure, for rotational failure in this case. And if your slopes are plotting within those zones, for the given geology that this considers, and this is in the high plasticity clays, you can map that straight across into the satisfactory and unsatisfactory state at this lowest level. And you can see it's a conservative methodology at the lowest level. So if you're in that zone in the middle where you've got moderate vulnerability, where it really depends on the absolute site conditions, we take a conservative view that that's an unsatisfactory state until you can prove otherwise. Thinking about rock slopes, Network Rail has a methodology called the Rock Slope Hazard Index, RSHI, within which is the classic hook and bray type wedge kinematic admissibility calculation. And at the lowest level of assessment, there's a measure within it called the FC max. And if that gives a value of greater than 0, it essentially means you're in a kinematically admissible state for wedge failure, and therefore it's considered an unsatisfactory position to be in. Whether in reality, as you dive into more to that, it might be that it is stable, but at the lowest levels, it starts with that assumption. A quantitative assessment is where you're actually getting a number coming out from some kind of analysis. In this case, just illustrating from the GSRA work, a limit equilibrium. So when we look to this type of analysis, the outcomes are measured relative to some reference value, in this case against a factor of safety, that you would have to define as part of the assessment. So if you end up with a factor of safety that is in excess of that reference value, you're in a satisfactory state. If you're below that reference value, then it's an unsatisfactory state. It hasn't gone as far as stating what that reference value would be, because that's going to vary job to job, the decision that's been made. So back in the day when you might have been looking for a factor of safety of 1.3 for analysis, we're not in that world within it. It's decided on a site-by-site basis. So another part of the assessment methodology is this concept of levels, and Mike introduced that quite well, is that from level 0 through to level 3 is you're moving up in the complexity of the method, the amount of information that you're gathering. Your surety is going up, your uncertainty is coming down, but the cost is going up. So you can rationalize the assessment methodology as having level 0 being a virtual assessor carrying out, it's fully automated using methods and data that is available for the Earthworks, but it's got the largest number of assumptions in the way that it's calculated, all the way through to the top level. Level 3 is when you're at the real high end level of assessment, and that's where we might be talking about finite element type analysis. You've got a lot of ground investigations being carried out, decent understanding of what the groundwater is doing, etc., which obviously comes with the greatest cost. We won't go into this in a huge amount of depth because I want to get onto more of the knowledge side of it and the geological concept constructions, but within the guidance in the module, we've gone through and we've carried out a detailed review of the types of analysis techniques, assessment techniques that can be carried out. They've been grouped together into sort of generic types of assessment. So, you know, GSRA plots are there, limit equilibrium, etc. They're related to the different levels of assessment, and then they relate back through to the type of failure mechanism that you're carrying that analysis out for. It's not as prescriptive as saying the types of software that would then carry that out, because obviously that's something that can change over time. But it does go through the current types of analysis techniques that can be carried out for each of these things, recognizing, of course, that, you know, that might change. So moving down to below the different techniques, the key thing we want to focus on now is thinking about how you feed those techniques with the knowledge that's required. And this is really where engineering geology has got the biggest part to play. So there are 4 bubbles that you can see they're associated with assessment knowledge. I'm going to start by talking through geological materials and how those have been related together into geological cohorts. And then Verity is going to take us through the ground models and the failure mechanisms and how they feed into the process. So, geological materials and cohorts. So the rail network that Mike introduced earlier, you know, 20,000 miles of network is interacting with 3,285 different geological materials as recorded by the British Geological Survey. So, you know, 2,500 bedrock materials, 600 superficial materials from their mapping. For us to go through and assess and use all of that information on an asset on a code by code basis is plainly not feasible. So what we've made use of right from the start in the GSRA methodology is using the BGS's lexicon RCS codes, which is the combination of the lexicon, which is the stratigraphic descriptors, and their rock classification scheme, which gives material classifications. We've used those as a means of grouping together different geological materials that have similar engineering behavior so that we can then consider the assessment against that level. So this diagram shows how that grouping together, that cohorting has been carried out. So from a consideration of all the materials represented by the geological map, we look at both the bedrock map and the superficial map. The bedrock essentially is then split down into rock, which is essentially, it's the stability of a slope in it is driven by the discontinuities within it, or on the other side of it, it's driven by the intact strength that's driving the stability. And out of that, 4 cohorts for rock come out: hard rock, mixed rocks, soft rock, and chalk. Okay. On the other side, on the superficial side, for most of it, but not an entirety of it, we've then got the soils, where we split things down into clay materials, granular materials, and organic materials. And the clays, I've got another slide which I'll come on to. We divide its behavior up by liquid limit and clay fraction. And then the soil, the granular soils is much more by grading in uniformity. You will recognize here the little dashed line coming across. Within the process, within the guidance we set out, we do take account of the fact that certain bedrock materials can weather to being in a soil-like state, and that's considered within the process and bringing them over into the clay cohorts. So the clay cohorts are subdivided according to essentially their plasticity behavior within a chart which has the axes of liquid limit on the x-axis against clay fraction content on the y-axis, building on work that's come from other asset owners through the years. It's been applied in London Underground, it's been applied by Highways Agency, as was, and essentially divides up the materials into cohorts that we've called the brittle clays. So that's essentially where you've got your high plasticity clays, slightly brittle clays and moderately brittle clays, and ductile clays within different regions of that chart. So by classifying materials within those groups, we can start to bring together typical geotechnical parameters that allow us to feed that into slope stability calculations and start deriving those slope stability charts. On the right is just a piece of work that's included within the guidance that compares that method of dividing clay materials up with one way of looking at it, which is around a bounding value of a PI of about 25%, where you can see that tipping point between materials behaving in a brittle manner with a drop in strength from peak to residual to moving over to materials which are much more ductile. And you can see it relates very well. The light lines show how that PI boundary would plot. What we get by doing it this way is a little bit more finesse in the way that the assets can be, the materials can be split up. So this is defined, this chart allows us to define bands around the different geological cohorts. And you can see there are examples of the types of materials that fall within those cohort names, which are kind of typical groups that I'm sure a number of you would have been working in over the years. I'm not going to go through this in a huge amount of detail, but one of the things that's also considered within the methodology is the potential for materials to weather from their bedrock state and then become either an issue as weathering to a soil, such as the over-consolidated high plasticity type clays that feed into that, but also that older mud rock and mixed rock materials can actually weather, and the biggest failure mechanism problem then becomes around the raveling of those slopes. So this diagram takes you through the recipe by which the codification applied by the British Geological Survey units feeds through into the cohort that each of the materials have been put into. And just to put in a bit more geology, here we sort of show that the bounding age for the potential for weathering to a soil is set at Carboniferous and younger, and then the older rocks, the more indurated rocks from that point are the ones which are considered to have the higher raveling potential. One of the big challenges with Network Rail's assets, given their age and the lack of records that would have been held for them, is actually understanding what they're constructed out of. So for cuttings, you can have a reasonable stab at what you're dealing with by looking at a geological map. When you're looking at embankments, obviously there's a lot more of a challenge. So one of the pieces of work that was done, the body of the work that's fed into this, was looking at trying to back calculate what the embankments are likely to be made out of by virtue of their proximity to cuttings nearby that would have provided the fill material for those embankments. So one of the early embodied pieces of work that was required to that was to look at the railway and back calculate how it was constructed. So we've got the engineer's line references which describe the individual routes. We did an early piece of work to determine the age of construction. And by looking at that, and this little example just shows how we would split this section of railway into 3 areas of construction. You've got one ELR number 1 that was got a date of construction of 1840. We can consider everything in that would have had some kind of mass haul balance. We've got another section of the same ELR that's got a different date, so we would consider that separately. And then we've got another one that was built at the same date, but it's a different part of the railway. So we split up the network into these little sections. We then made use of the geometry information that came from LiDAR surveys of the network to try and determine how much fill was generated from the cuttings around the network. So in this example, we could simply take the ground surface, like denoted by the brown color. We could take the network boundary, consider that the ground surface would have been like that, calculate the volume of material that could have been dug out. On the other side of the calculation, we can work out the size of the embankments and the volume that's associated with those. We can then, this is a complicated diagram, but I'll try and explain it. We can then try and determine what materials came out of those cuttings by superimposing the geological information from the BGS onto that section. So in this case, units A and B are in the superficial map, so 2 different materials. The thickness is bounded by those red lines, for which we use the ASTM model, the superficial thickness model from the BGS. And then the bedrock geology underneath that is units C and D. And by applying that thinking across the whole network, we can get as good a calculation as possible of the materials that would have been dug out of the cuttings. And we can then apply them through a GIS procedure to keep filling up the nearest embankments until the volume of the fill from the cuttings is used up in the embankments, including an element of the bulking that would have occurred and the lack of compaction on the other end. And then because we get these calculations at discrete sections along the network, we can extrude that out onto the entirety of the length of the network. And then through that calculation, we can bring the geological materials of the nearby cuttings into the embankments. So it's almost like a back calculated mass haul calculation. Okay, at that point, I'll hand over to Verity to talk us through the next sections.
Hi, good evening, everyone. Yeah, I'm Verity Wadesmith. I'm a technical principal at Mott MacDonald, and I was actually the Mott MacDonald project manager for the work that we did that went into this. And I'm just going to go through with you those last 2 bubbles that were ground models and failure mechanisms. So as part of the task, we actually got to define 20 generic ground models, and these were related to 12 to cuttings and 8 to embankments. Each of these were defined, we had either by, there's a little schematic there in terms of whether they were natural ground, made ground, but also with the material boundaries, noting that ground models is invariably just, there's so many different ones that you could possibly have, and the variations, we really needed to simplify this down just to have something that was available and that had that variation within the definitions of them as well. So really, like I said, as part of this level 0, kind of level 0, level 1, when you don't really have a lot of information and it can be applied across the whole network. The ground model is actually assumed, as an example here for cuttings, was as a single material. As I said, there was 12 different ground models for cuttings. And so you can see there on the right-hand side that where, get my laser out, we've got the variations there where you can have interbedded materials underlain, overlain by a single material. But noting, as I said, the enormous amount of variability you could get with this. We also included where you could possibly have your weathered material, weathered layers on top, but of course these could be various thicknesses, various dips, all sorts of options. So we tried to make these as kind of catch-all as possible. So as part of that as well, we had lensoidal inclusions there on the left-hand side as a cutting, but also thinking about all of these, we had to try and cover everything that was all eventualities and all the different geologies that we had as well. So allowing for one for chalk infill, etc., for example, with incised inclusions. So with the embankment examples we just got here, so again with the level 0 approach, you would assume that it would be a single material and your embankment with underlying material and the ballast at the top. Again, with this, with the variations, you could also have soft materials at the bottom. Again, the thickness on these, the variability of the original ground kind of profile as well. Move into more options, like with more complex, and as I said, as your information and your knowledge increases through the levels approach, your ground model can develop as well. And whereas you've got options, particularly maybe where you understand and know that the embankment has been widened or added to, you might have a blanketed face with raised cores, or as I said, again, the option where you've got this potential soft material underneath as well. So that was kind of a common theme through that. And we tried to cover, like I say, a lot of eventualities in that. And then moving on to the next kind of knowledge assessment knowledge bubble, as we're calling them. So it's failure mechanisms. So as part of this, we've defined 19 different failure mechanisms, and these go from falls, slides, flows, settlement, and collapse. Or if you have one or more of those, which you might do in many locations, we would define that as a complex failure mechanism. Now, the really important part of this was that there's several definitions. There's many different publications at the moment that already include and are very comprehensive on failure mechanisms. But really, a lot of these are related to natural slopes and not particularly to infrastructure slopes. So it was really important to bring those together and define those for Network Rail's assets, but also making sure that existing terminology for Network Rail and practices were included as far as possible. The really important part of this as well is to make sure that the same things got the same name. The amount of times that two different people can call the same failure mechanism different things, it's really important as part of the process to make sure that these are really well defined and people are using the same terminology. So in the standard, what we've got is they're all well defined, and I'll show you an example in a minute. But just to point out that an important part of this is trying to understand the speed of failure. So that helps as well, trying to understand like what you might need to do or the knowledge of your site. So again, there's just some additional information there on the different types that I probably won't specifically go into those, but there's lots of common terminology that you'll see and understand there. But again, really important part is the same thing. It's called the same thing by different people. So as part of the standard, within the appendices, there are detailed descriptions, examples, some notes, also some real life examples from out on the network. Something as well which is important, and I'll come to on in a second, is the applicability of that failure mechanism. So it's all about how can you understand what failure mechanisms are likely, so which ones do you need to assess or look at in more detail as part of your assessment. So, like I said, a lot of the failure mechanisms, and you'll see with a lot of the work that we've done, and we've related everything back to failure mechanisms. So once you know those, you can use the tables and charts to understand what assessment techniques you can do at the different levels to understand what the likelihood of those failure mechanisms are. So linking those to assessment techniques, what we've also done is all of those, once you understand your potential failure mechanisms and your assessment techniques, sometimes instrumentation and monitoring is obviously a really important part of the process, and will give you that more information and knowledge and to feed into your assessment. So again, with there's lots of these different applicabilities that will show you. For this, we've been able to link the failure mechanisms to like I say, instrumentation for ground movement and groundwater monitoring. So it's like various different techniques that you may wish to consider related, as again, specifically back to those failure mechanisms. So with like I say, the applicability matrices, the cohorts, we've mapped all the cohorts to potential failure mechanisms. So if you think about that knowledge and those bubbles as you move through the process, you understand your geology, you can link that to your cohort. From your cohort, you can understand your ground models, and then again, what are the potential failure mechanisms? So with this, there's a generalized applicability of the potential, once you know your geology and your cohort, what are the potential failure mechanisms that you need to be looking at as part of your assessment. So we've done that related to, this is one example related to cohorts, but as I said, it's also related to your ground models as well. So it's building that picture of what are the different considerations that you need to do as part of your assessment. So we've mapped it to the cutting ground models and also to the embankment ground models there. So that's kind of covering all of our bubbles within our assessment knowledge. But something really important as part of this piece of work that was done as well was to improve, one of the activities you can do is geomorphological mapping. So there's some, the idea was that as part of the guidance that we included specific guidance on the use, the value of good geomorphological mapping, that the information that you can gain from it is really important towards your assessment knowledge. So the idea of the standards was to include some improved guidance, which includes roles and responsibilities, and what are the competencies and that people need to be able to do this mapping, the procedures. Also going through, obviously, with the technology and the benefits of there's so much more desk-based and remote survey information, so making the most of that, as well as validation or additional information from field-based. But then also thinking about improving the terminology, keeping things common and consistent. So there's actually some symbology and actually the reporting requirements behind that. And of course, some best practice examples in there. So this is just examples here of, we have our process there on the left-hand side, what we can do, the steps you need to follow, and how, if you need to go to site, have you got the information, what more can you add? And like I say, an example there, just to show the kind of, get that consistency from suppliers and the supply chain in terms of that, because the value of a good geomorphological map, well, I'm preaching to the right people here, aren't I, and geologists, so there's just some information in there as well. So now I'll get to hand back to Mike.
Thank you. So last few slides. So where we're up to is all of this new content that we've heard about tonight is encapsulated into the new 086 standard, which was published last year, and it has a compliance date of this year. So it doesn't actually require our route teams to do any assessment, but it requires them to set out what their appetite and desire to do assessment is in a regional earthwork assessment strategy. And if they agree with Lord Mayor's recommendation that assessment can benefit evaluation and prioritisation, then it will set out an assessment programme. And the only way that we can really fulfil that, Network Rail can't do it on its own, we need the help from the supply chain. So it'll involve, hopefully involve some people in this room. If we initiate a large-scale assessment programme, it can't be a ungoverned Wild West type situation. So there are some basic minimum competence requirements in the standard for the lead assessment engineer, i.e. the person leading a team that's undertaking a level 2 or 3 assessment, which is shown in the table there. Good news, we've got the Joel Suck in as one of the one of the valid charter ships, so that would have been awkward. I think I said this earlier, but level 2 and 3 assessment, the sort of traditional form of assessment, we haven't tried to fundamentally change that. We're really augmenting it with the lower level assessments that can be executed quickly at higher volume. But it is a slightly different perspective to when designing a new earthwork. This is the procedure in the standard for level 2 and 3 assessment. And once the lead assessment engineer has received the remit, they've got to do a desk study, of course. but everything else from there on in is optional. Even going to site, and that created a lot of controversy with someone in the front row. Is considered an optional step, as is the geomorphological mapping, GI, and monitoring. What the assessment engineer is asked to do is address the question at every step: do I have enough information? Is my ground model refined enough to actually apply an assessment technique and get a valid answer that could help the network rail evaluator make a better decision about how to manage this earthwork? So the other thing to draw your attention to is, you know, we are trying to standardise the terminology. We've used desk study and site inspection because the second generation Eurocodes do, and then I think you know, site investigation becomes ground investigation, and so on. Another place where we can affect some harmonisation is how these level 2 and 3 assessments are actually delivered, in terms of how the deliverables look. So a template is defined in the standard for what an earthwork assessment report looks like. And again, this won't fundamentally change. We still expect to receive a report and associated files. The difference is, instead of zipping it and emailing it or FTPing it or whatever, we're aspiring to update our earthwork asset management application online, so that when an assessment is completed, it can be uploaded associated with the earthworks that were in scope. And there's a form that's filled in that contains all the relevant metadata about the assessment, such that all the assessments become searchable, no matter what level of assessment it actually was. So yeah, just a few things there on how we see the supply chain helping us. And that is the last slide. So yeah, thank you for listening. Are there any questions?
I have prompted for questions online, but haven't had any come through yet that I can see. So start with questions in the room. Got some microphones. If anybody's got any questions, put your hand up. And
Scott O'Neill, thank you very much for the talk. I'm interested, and I think potentially you've partially covered this. How does this apply where there are earthworks with previous, perhaps unrecorded fixes that are showing problems?
So at level 2 and 3 assessment, you would take it into account in the way you traditionally would. At level 0 and level 1 assessment, when you say unrecorded, you mean like a retaining wall was built and we've forgotten about it?
No, a slip that's perhaps been a slipped area that's been rebuilt and perhaps was revegetated such that you can't see automatically that it's a man-made fix.
Yeah. So you're talking about the material parameters? Or...
Yes, and how does that fall into how you've captured this in the process you've generated?
Yeah. So at level, maybe I've got an example actually. At level 0, allow me to illustrate by example. This is a major embankment at Hook, which failed 2 years ago and severed the connection to the southwest for I think it was a couple of months. Just there's an aerial photo of it. You can see a section that previously failed and was repaired, and the section that failed this time is a bit sort of closer to me. So this is the view from the track looking the other way. Here is the digital terrain model from aerial survey. I don't think HS2 are going to profile earthworks like that one. That is an absolute mess of previous failures and fixes. So the pin is where the failure occurred, and that's at the intersection of 2 of these earthwork 100-meter segments. And when we apply, if I just skip to the application of a global stability appraisal, this slide shows all of the stability lines, which mean factor of safety equals 1, from the library that would be applicable to this earthwork based on the geologies that we've estimated are present in the embankment core. Now, each of these lines is based on a set of assumptions about the material strengths and the things like poor water pressures and so on. So where you've got evidence of previous failure, that is crucial information at level 1 in the selection of the most appropriate stability line, because at level 1 you can only choose, there can only be one line that you choose to be on the stable or unstable side of. At level 0, which was Chris's illustration, there's so many assumptions. We use 2 lines and say there's a moderate vulnerability zone in the middle of them, but both of them mean factor of safety equals 1. They just represent different sets of assumptions. So it's an inexact science, but I'm keen to point that out to everybody. The level 0 and level 1 assessments can't rival level 2 and 3 for accuracy, but instead of assessing 10 or 100 earthworks, we might have an answer for 200,000, even though it's an answer we have to revisit by moving up the levels.
Thank you.
I just add a further point to that, because it is an interesting point that Scott's raised there. So when you apply the GSRA plot to high plasticity clay slopes, the stable zone only filters about 30% out, I think, being in that. So there's a whole swathe of them that are in the moderately vulnerable and the high vulnerability zone. In the high vulnerability zone, there are a lot of Network Rail's assets sit in that zone. If you actually look back at Tim Spink's keynote speech from 2017, that's was in QGH, that asks the question why in that top right zone, where there's hundreds and hundreds, thousands of assets, not all of them have failed. So why? What's going on with the number that, why are a number of those not failing? There's stuff buried in them. There's, on the Great Western Railway, the track that was taken up was cut up and banged in, wasn't it? There's a whole load of things that are going to be holding up the assets that we might not even find out at level 2 and 3, I suspect. But it's a very good point. Yeah.
Great, thanks, Scott. Any other questions yet, Chris?
Cheers. Chris Cox from Atkins Realis. So just with the level 0, level 1, is the idea to apply that to all assets, so including sort of going back to the original EHC ratings. So how do the sort of level 0 assessments compare to the existing EHC ratings?
Give me a few years to figure that out. No. We're looking at the portfolio through a completely different lens. The bottom-up stability, the pure sort of soil rock mechanic considerations, and we get an answer that isn't palatable to most people, which is that around 80% of earthworks appear to exhibit some instability that we might question, can we tolerate that? With EHC, we deliberately set the boundaries so that it was a prioritization system. So that half the assets are in A, half of those are in B. You only have sort of 5% of assets in D and E. So when you actually compare when you multiply the sort of failure rate by the number of assets, you actually expect most failures in C. So I just wanted to give that background. In this case, because we've got so many things looking unstable, I would expect most failures are actually of theoretically unstable assets. Now, the next thing we have to do to make that geotechnical risk register quantitative so that we can actually sort it is to convert the assessment outcomes into things like a time to failure or a 1 year a hazard rate or a probability of failure in 1 year or in one control period or so on and so on. And that's the next piece of work that's going on at the minute. And we've brought in some mathematical consultants to help us with that. Again, there's a lot of assumptions, but what we want to do with that methodology is make the uncertainties and the assumptions explicit so that we know we're making a decision on this piece of information and we can trust it to this extent. So there's a lot of work to do to reimagine EHC, which is now 10 years old. But at the moment, they're 2 parallel systems giving you a different lens on the portfolio. Thank you.
Any other questions in the room?
Ethel Cortegana, Network Rail. When you explain about the back analysis to estimate the volume for the cut and fill, what is the assumption for the shoulders? Is assumed that the embankment has everything is made of the same material, or you would distinct core and shoulders?
Yeah, this might be useful for that as well. So the actual geometry is taken from the terrain model. And if you follow the methodology that Chris was describing and apply the cut fill balance, and I think of it as sort of like a re-simulation of the original construction, you end up with a result like this. So these are the two assets that were affected by the hook failure. I think you can see the first 3 rows have got the same code, and the second 3 rows have got the same code. You can see that about 50% of the assumed material is ductile clay. That's what I think that's right, isn't it? That's what that code is.
Yeah.
About 40% of the material is the brittle clay, and the rest of it's granular soil. But when we apply the level 0 assessment, we don't know how that's configured within the cross section. So the ground model at level 0 is just a uniform single material cross section for embankments. For cuttings, you've also got the weathered version, and we'll basically assess it 3 times, the same cross section, and say, right, it's entirely granular, it's entirely brittle clay, or it's entirely ductile clay, and that's what these stability lines are. So we've got the rotational stability of the brittle clay, shallow translational stability of brittle clay, shallow stability of the ductile clay, that you don't need a rotational assessment for that, and then shallow stability of the granular soils. At level 1, I haven't got anything to show for that, but what I expect we're going to do is allow people to divide a cross section into facets and apply the assessment to each facet individually and to the overall geometry as appropriate. Because if I think about cuttings, one of the main limitations of the use of the National Aerial Survey and the LiDAR and the terrain model was with what I ended up calling biangular cuttings, where you've got a sort of competent rock overlain by maybe like a glacial till or something, and there's a pronounced change in slope angle, and we've just got an overall characteristic line joining the toe and the crest, and we're kind of overestimating the soil slope and thinking it's more unstable than it is, but we're underestimating the rock slope. So that's for the level 1 assessor, i.e. the evaluator, to unravel as the best they can, and if there's still too much uncertainty, then they can commission a level 2 assessment.
Okay, so the recommendation would be to consider that we have a to use the GSRA plot, the geomorphological plot, we could consider the material in situ, assuming that has been filled with material from the cut, and then to run assuming that material is imported based on the description on site, for example. We could run these 2 cases. Yeah,
it's geotechnical engineering. We've got to have sufficient flexibility within the methodology. You could look at this and say, there's no granular material here. That's nonsense. I'm discarding that assessment. I think this is purely a clay fill embankment.
Okay, thank you.
Yeah.
Hi, Michael Vance, Mott McDonald. At any stage during the rewriting of the assessments, did you consider moving away from 100-meter lengths into whole assets? Sorry, I used to do highways, so.
No, I consider that every day. Yeah, I think there's a whole earthwork church, and I call them 100-meter segments here, but internally we call them 5 chain lengths, which is 110 yards, approximately the same. I think they work for different purposes. So when the teams 20 years ago were trying to figure out how do we just get like a baseline survey of the network, it made absolute sense to divide up into consistent chunks. Now when we're thinking about assessments, I think you've got to take a whole earthwork perspective. So in the guidance, and this is a key change to evaluation actually, you might be driven to do an evaluation by something that's going on with one of the segments. For example, exceptional track geometry deterioration. But what you must do is decide whether to extend your evaluation to the adjacent segments. Whether it's the whole earthwork or not is another matter, because some of them are quite long. And accordingly, the assessment can be applied to more than one 100-meter segment. It might be that one cross-section typifies the geometry of 2 miles of track, but it might be you need 3 or 4 cross sections for, you know, a short length. I think this is I think that's a good example, isn't it?
Yeah, it's quite interesting, that question, that Mick, because as you know, for national highways, it's done differently. It's done for the whole asset. But then when you actually want to dive down to do certain things, like, for example, determining relationships between what you know about drainage in an earthwork and the assets, it's a lot easier in 100 meter. And in fact, that's how we did some of the initial drainage policy work, because it was in 5 chain lengths. You could actually then relate it to drainage records, which were in 5 chain lengths. And then actually for national highways, when we did some work to assess deterioration of the assets, we split whole earthworks up into, surprisingly, 100-meter lengths, because you get benefits. So actually there's 2 sides to the way that you could do it, and both have got advantages and disadvantages. So I don't think there is a right answer, to be honest, to it. There's pros and cons to both.
Hi, Rob Tolby from MOTS. The new assessment model creates vulnerability charts that have been created very much from first principles. When you've then created those charts, how did you then proof the charts and the findings? Or you just take us through that, because I'm sure you did. Maybe historical records?
Didn't your team do this work?
I'm just trying to elaborate the conversation, really, and help explain what Chris and Verity have done.
So yeah, defer to Chris. I was just going to say, Chris, if we put the geomorphology,
that's exactly what I was going to say,
for brittle clays, all the failures are in the high vulnerability.
Yeah.
If you move back across the cohort scale, it's a little bit more mixed. But
you would find hardly any, if any, I can't remember, in the safe green zone failures. So it's basically the calibration against quite a large number of failures, particularly in the brittle clay cohorts. They are all in the high vulnerability zone.
Yeah, so if there was a QA sheet at the end of the report, it would show that plotting. And that would prove that the vulnerability charts do match historical data. Yeah, that's fantastic.
The greater challenge is the thing that goes back to Scott's question, is what about the dots up there that haven't failed?
Yes.
Why haven't they failed? That's the really interesting.
But that's your next stage of R&D and progressing. Yeah.
That's the level one where, you know, the evaluator can see, the automated procedure's been a bit confused by the Gabion wall at the toe there. This is the true slope angle. The asset doesn't really plot there, it plots here. Or, you know, it could be, this is a vegetation critical earthwork. Do not chop the trees down, line side colleagues, please.
Just thought of another line of validation. So those of you that might be aware of the Achilles research program, which looked at long-term stability of particularly high plasticity clay slopes. One of the things that they did through the steering from industry of that work was to plot their results against the GSRA charts, and they are nearly identical from the very, very high-end modelling that was carried out as part of that. So there's an extra level of validation that's come out of that R&D type work as well.
Brilliant. Thank you very much, Chris and Verity. Mike?
Hi, Anna Morley, the chair of eggs. So thank you very much for coming out, especially so soon after Christmas, and talking to us, and really good turnout in the room. Thanks very much. So my question is, what does success look like for you in sort of 10 years' time? What are you going to look back and think, and how are you going to measure it?
Yeah, so I've not included any of that, but we have a whole suite of leading and lagging indicators that tell us about our performance in management of earthworks. So just to just to cut to it, I would expect to see those indicators trending the right way. Can we pin that on specific improvements here versus everything that's going on? There's all sorts of changes going on. We're getting more people, they're getting more competent. We'll probably move away from a reliance on people gathering the data and expect to see INSAR and aerial survey being the norm. So that's kind of like the long term, reduced failure rate, intervention effectiveness, intervention targeting, all this kind of thing is improved. But sort of leading indicators in the next few years, we just expect to see some assessments actually happening. And we really need to get the programme kind of off the ground. Did you want to say anything additional to that, Chris? Or
No, I was going to make that second point. It's absolutely it's seeing people picking it up, making use and embracing the standardization of the reporting means in the way that the industry has. Everybody knows how to do a 622 report for national highways. It's just it's spread throughout the industry. So just to see that level sort of engagement with it and making use of it would be the initial success.
And a specific thing I would like to see is assessment used as a tool to disprove the need for work. Because I think I'm just going to quote David Anderson: the best value assessment is the one that shows you don't need to do anything. Because we've got far more candidates than the volume budget that we're funded to kind of deliver. So assessment is surely going to help us prioritise better, even before fully integrating it with EHC and all the rest of it. I'd like to see some evaluation decisions that say we're not going to do any work here because we've completed an assessment to this level and we're satisfied that the risk is tolerable with respect to such a failure mechanism, which means we can use the budget elsewhere.
We've got some questions online and I'll come back to you, Luke. So yeah, first one here online from Mark Wheeler of Binnies. So he says, factor of safety was mentioned as part of your presentation. How is this approached in light of the Eurocodes? One might suppose that applying Eurocode may say an asset fails, whereas using an older global factor of safety approach, the asset is found to be stable.
So I would say the answer to that is the reason why we didn't put a number is because we exactly went down that route. Is, what you've got different ways of looking at it, different camps about how it could be done. So rather than us try and wade into that unresolved argument and say it should be, factor of safety of 1.3 or whatever, we stayed away from it by making that still, and we did debate this quite a lot. We stayed away from that by saying, at the job basis, the person commissioning the assessment needs to be saying what's their requirements about how they want to do that.
Yeah. So, and the other thing is, this is assessment of legacy infrastructure earthworks, not design of brand spanking new earthworks. So there is a clause in the standard which, with respect to the resistance and actions partial factors, just says forget about it. You're at liberty to do as you wish. And as Chris said, the assessment remit is a very important part of this at level 2 and 3 assessment. And that is where the satisfactory, unsatisfactory determination is made on a case-by-case basis for the quantitative outputs at level 2 and 3. And you would expect there to be some, regional norm for that, established over time, but at the minute, we can't set a national threshold.
Thank you. Another one from online. We've got Angus Wheeler from National Highways. So First question is, how is groundwater drainage failures brought into the models?
So there's in terms of the failure mechanisms, there's an explicit section on flow failures, washout being surface water driven, and then we've got seepage failure being groundwater driven, and then there's the resultant sort of debris flow and mud flows. Interestingly, the worldwide literature review didn't uncover too many options in terms of assessment techniques for flow failures. There's an awful lot there that's there from the world of dams with respect to seepage failures, and there's an awful lot with respect to the calculation of run-out distances, but the actual vulnerability of the earthwork, there's not a lot there. So the extensible framework is, I hope, going to absorb some more techniques for flow failures over time. Sorry, the
groundwater side of it. So within the GSRA methodology for looking at translational failure and rotational failure, groundwater conditions are inherent in the modelling that was carried out that derives the suites of lines that come out. Yeah. So the biggest separation between the lines with similar parameters in that comes purely from the water condition that's assumed in the model. Yeah. So, and that's set out within the guidance about how you account for that. And embankments, it also includes assessment of whether there's under drainage due to a higher permeability material underneath an embankment. So groundwater is sort of actually we didn't make enough of that in the present as we were going through and presenting it. And that actually came back from Lord Mayor's group when we presented it as well. And we had to, so we haven't learned, but it is inherently considered in the modelling that was carried out for GSRA essentially.
Thank you. And sorry, you're going to say
just what Chris was talking about, the separation of lines. So this is an example of the brittle soils. So the cluster of lines on the right, that's one set of drainage assumptions. With the variation in the material strength assumptions, and then the cluster on the left is a different set of drainage conditions and the same variation in the material strengths. So in terms of GSRA, which bear in mind is one technique in this whole framework, there's a great sensitivity to what you assume about groundwater and poor water pressures. These were all modelled in slope W, weren't they? Using the hydrostatic line approach. So I think this is 40% and 70%.
Great, thank you. And another question here from Angus Wheeler, National Highways. Regarding the competencies, have you considered using the RoJet grades?
That was discussed. Yeah, I just refer back to there were lots of working group discussions about what the right solution should be, but ultimately RoJet was discounted. That's not to say that it couldn't change in future.
Same conversation was held when National Highways rewrote its standards, as Angus will know, around whether that was included or not, and the same decision was made at that point as well.
Thank you. Got a couple more online, and then we'll take some more from the room if there are any. One from Alan Williner here. Where a new earthwork renewal is identified as being necessary, do Network Rail require a ultimate limit state margin of safety in line with new build earth structures to Eurocode 7? Or is there scope to provide a margin of improvement below this to improve more locations and avoid spending a lot of money at one location only to find another location along the track? That then causes the future maintenance interventions.
So when we were doing this development work, at the same time, we had a parallel set of working groups working with the teams working on the second generation Eurocodes. And that culminated in the republication of another standard in the civil suite, 071, which is geotechnical design. So that is true to the Eurocode intent. We haven't Network Railified the design approach. So you could look at that and say, then assessment and design are sort of uneasy bedfellows, not quite compatible, and I would accept that to an extent for the time being. If I go back to Earthworks procedure that Lord Mayor was quizzing us on. This is a tool that comes in much sooner than design. But yeah, 071 has also been updated, which is, well, Ronnie in the room knows a lot more about it than me, but I think I'm right to say, Ronnie, it's kind of fully aligned to 2nd Gen Eurocode 7, isn't it? Yeah.
A couple more questions here online. Question here from John. Are we any nearer to when slips will occur? In what year or even what decade? As that is the budgetary question. What a question.
There's a good question, isn't it? So Mike started alluding to some other work that's going on at the moment, trying to move into a world of producing an algorithm whose output is a survivability rate within which measures like that of, you know, is this slope likely to survive the next year, 5 years, 10 years against a certain probability, is part of that framework. So are we nearer by virtue of the fact that we are at least trying to embrace that world? Yes. Are we nearer to saying whether it works or not? Is work in progress, I would say.
Yeah, and the other thing I would say is the volume and velocity of data is increasing. So Hook is one of our embankments. There's 100,000 100-meter segments, 50,000 of them are this EHCA. They're examined once every 10 years. So once every 10 years, a person goes and looks for 20 minutes. We're rapidly moving to a world where you've got INSAR data every 6 days. You've got a train-borne survey every month. You've got precipitation data being updated every 5 minutes. We've got extensive instrumentation that's giving minutely values. I think if if we can actually master the federation of this data, it doesn't, it's not going to, it's not a magical solution, but it starts to underpin the answer to questions like that. How long has this earthwork got left? What probability is it going to survive 1 year, 5 years, 10 years? In a way that I think it would be reaching a little bit with the current sort of inspection approach.
Just to throw into the mix to make that even more complicated, of course, is the fact that the climate is changing so considerably. And that then adds another level of variability into any predictions that we might be making. So, even the steps that are being made by the Achilles work and work that we did for national highways to sort of increase deterioration rates based on climate change variables, that's still very much another area of variability on top of the variability that already exists. So it's a challenge. I think, well, it'll keep us going, give us something to do at least, won't it?
Yeah. Yeah.
And I think last one from online, it's from Lee Parry, I think Mott MacDonald as well. And actually just a clarification, it seems, good clarification on pore water pressure. From memory, the red lines on the right are for RU equals 0.2 and the green on the left are RU equals 0.35. And the difference between the two outweighs the likely variation in strength parameters.
Yeah, so Lee is was the overall technical lead for this work. So
I think his word.
Yeah, I won't argue with him.
Yeah, thank you, Lee.
But I think in the report they did. I think they used the hydrostatic line approach and then converted it into an RU value. But yeah, the point is made. It's far more sensitive to drainage than anything else.
Hi, Luke Johnstone, Atkins Realis. You already answered my question on the changing environment, so I'll ask another one. You have a huge amount of historical data on geology, ground investigation, failures, etc. And as you said, the velocity and amount of information coming in is increasing. Are you looking at any machine learning or AI solutions to, especially at that level 0 assessment?
I'm not, because I don't understand it. No, I think, yeah, the next generation of engineers coming through are going to really pick up that baton, aren't they? I'm not jumping ship just yet. But whenever anyone mentions sort of ML AI, I just think I know what our data looks like, and it's not fit for that application just yet. But when you do start to see, sorry, I'm it's a good job we put this in, isn't it, Chris?
It's very good, yeah.
The geometry information that informed the level 0 assessments came from a geospatial procedure that was applied nationally to the terrain model. And the person that did that, he said to me, okay, it might not be 100% accurate, but it's like the same person examined the whole network. And that just gets us one step closer to having consistent, dependable data. And there are lots of steps happening right now that improve the reliability of the data that we've got. And I think we will be in a position soon to start to apply that. But that, I always think that's at the end, once you've done the real hard work, the real hard graft of sorting the data out.
So there's a couple of things that I would add to that. One is R&D work that's going on at the moment is looking at application of data science techniques like Bayesian methods to allow feedback of constantly updating data to feed its way into the predictions that you're making. The other thing about application of methods like that is that I've seen a good example of data in this sphere being provided to researchers using neural network methods, reporting back to us. We've got a brilliant correlation between all of the input data and this output RSHI value that you've got. This is what we want to do. To which my answer was, there's an algorithm that takes those and spits that out. And so you've learned nothing. The only thing that came out of that came about because there was a massive disconnect between the world of mathematicians and applications of machine learning and AI, divorced from the domain experts who understand the data and the problem that was feeding into it. So there's a lot of people flying around. How many adverts do you see on the radio and listen to it talking about AI this and AI that, and you're going to get this? And if you divorce, if the data science world doesn't connect with our world to make sure that the problems are being answered in the right way, we're not going to make advances. But if we can marry the two together, then there's absolutely a place for it. One of the big things that I'm sure is making a huge difference to the stability of Earthworks is what the vegetation is doing. So at the moment, the assessment of vegetation during current exams at the moment might be up to 10 years out of date for a network round exam. But we're not a million miles away from making use of image recognition to get, really almost, very, very rapidly updated characterization of vegetation. So if that's driven from experts doing that in the right way, that's going to feed into a bigger picture, and then we can make some real advances. So it's coming along with the fact that we're going to have to, it's getting harder and harder for inspectors to get out onto the rail network, get onto the motorway network. We're going to have to embrace these things.
Yeah.
Great presentation. Thank you.
Just got one more question come in from online. Is there any room for accommodation in the material classification system for relic shear surfaces within the weathered mudstone or cohesive soils?
Not within the material classification per se, but within the modeling techniques, the rotational stability models include the effectively the weakened basal layer model that's within the LUL guidance. It builds on that as a means of doing it. So it has a zone of weakened strength, which effectively could be considered to be part of the relic shear surface in that sense. When you get into the nitty-gritty detail, though, that's when you're in level 2 and 3. That's when you're into bringing in, if you've got solid fluxion, associated with the area that you're in, which can reduce friction angles down to very, very low angles, then that comes into you go for it, Tim. Yeah.
I'll just throw my shear surface bit into it. What the classification says is brittle clay. Warning bell. Okay. Yeah. And my advice to young geologists in the UK is, if you're in brittle clays, assume they're sheared until proven otherwise. You're right 9 times out of 10, they're almost certainly sheared. It's maybe rather difficult to find them. So I think the system and the classification rings that warning bell by it's brittle clay. Think about shears, and prove they're not there, which is more difficult.
Thanks, sir.
Great, thank you. Any more questions in the room? Let's see if I've had something pop up online. Yeah, no more questions online. Just lots of thanks for a great presentation.
Thank you for listening.
Yeah, thank you all for coming to attend in person today, and thank you to everyone online. I'd like to just say thanks again to our presenters, Chris, Verity, and Mike. So, round of applause to you. Thanks, everybody. Yeah, and we can close the meeting there. Thank you.
Yeah, thank you very much. I was a bit worried about that. So, you know, coming back in 4 days, not being ready for so I was thinking,